What?
662 got canceled again on Tuesday. So it's just
Like next week? Yeah, wow.
Next Tuesday?
She's like sick right
Okay, so transformations of joint random variables, and yeah, this sort of thing, it involves Jacobians, and I always hate anything that involves Jacobians, but
I am an engineer.
but today, as I said, first thing we're covering is when you have two random variables, or for that matter, more than two random variables, and you define functions of both these random variables to some new random variables, and you want to find the distribution of this new u and v. We're going to assume that it's one-to-one and differentiable. So that implies that this inverse mapping exists where you can define x and y functions of h and v, or functions of u and v. That I think there's a way to do this, even if it's not necessarily one-to-one, similar as we saw in the one variable case, but it gets even hairier than we have here. And honestly, in my experience, it's not something that I use very often. But given that it's one-to-one and differentiable, if you want to find the joint density function of u and v, you can find it by taking the density of x and y, substituting in these inverse mappings, and multiplying by the Jacobian, which, if you don't remember the Jacobian from multivariable calculus, that basically given this is h1 and h2, you take the partial derivatives of h1 with respect to u and v, the partial derivatives of h2 with respect to u and v, and put it in matrix form and take the determinant. So an example of this, say x and y are independent normal random variables, and you do this funky rotation where you multiply by sines and cosines and stuff like that. Then we're going to show that this rotated u and v are also independent normals, 0, 1s. So the range of x and y is R2. Both normal random variables can take on any possible real number, which implies that the range of u and v is also the full R2. And if you solve for x and y in the above expression, that's just a system of two equations, so it's kind of painful algebraically, but not that hard to solve. You end up with x equal u cosine theta plus v sine theta, and y equals minus u sine theta plus v cosine theta. So once you have that expression for x and y, it's fairly straightforward to compute the Jacobian. That you end up with cosine theta, sine theta, you can see the expression there, and conveniently you take the determinant, you get cosine squared plus sine squared, which of course is equal to 1 if you remember your trig identities, so when we multiply by the Jacobian, it's just 1, which makes our life easy. So that tells us that the joint PDF of x and y, since x and y are independent, you can just multiply the marginal density of x times the marginal density of y, end up with 1 over 2 pi e to the minus x squared plus y squared over 2. So to get the joint PDF of u and v, you substitute the expressions for x and y from the previous slide, multiply by the Jacobian, which is 1, and simplify that expression. Again, the sine squared plus cosine squared equals 1 identity helps us out here. We end up with e to the minus u squared plus v squared over 2, which of course is just equal to the product of two normal PDFs with respect to u and v. which tells us that U and V are both independent normal 0, 1s, as we were trying to prove. Make sense thus far, more or less? Okay. And there's this theorem in Cassel and Berger that says if x and y are independent, and then take any two functions of x and y that you can call g of x and h of y, those are also independent. The proof of that is relatively straightforward, so I'll describe it briefly. Let's define the event a sub u to be the set of x's such that g of x, the transformed version of x, is less than or equal to u. B of v is the y such that h of y is less than or equal to v. So the joint PDF of u and v, by definition, is the probability u is less than u and v is less than or equal to v, which of course is just the probability that x is in a sub u and y is in b sub v, based on the way we defined a sub u and b sub v. And since x and y are independent, we have that theorem earlier on that any possible event that we can define in terms of x and y are independent. That's the probability that x is in a sub u and y is in b sub v. And, well, because I never even wrote the punchline here, that shows that the joint PDF of u and v's is the product of the marginal PDF. No, the reason I didn't write the punchline is because I'm still writing the proof. Sorry, okay. So the joint PDF of u and v is just take the partial of this joint CDF with respect to u and then with respect to v. And so from the previous slide, we showed that that's the probability that x is in a sub u and y is in b sub v. So we take the partial of the first piece with respect to u and the partial of the second piece with respect to v. And the first piece only depends on u, the second piece only depends on v. So the joint PDF can be split into two pieces, one which depends only on u, the other which depends only on v. And as you'll recall, we have the theorem that says u and v are independent if and only if the joint PDF can be split into the product of the marginal, so they're independent as we claim. Now let's take a slightly more complicated version of the previous example where we multiply both u and v by a constant a. And we want to show that in this case we end up with two independent normals with mean 0 and variance a squared times sigma squared. Oh, in particular, if we let, oh, actually, I guess, sorry, I should have reviewed this more carefully last night. What I was trying to say there is, based on this previous results, we already have that if we changed, in the previous example, we took them to be normal 0, 1. If we just assume that they have variance sigma squared, then they would be normal 0 sigma squared. We multiply them both by a, then by formula earlier, we multiply both variances by a squared. So as we did above, we have normal, we have the u and v are both normal 0, a squared, sigma squared. They're independent of one another. And now we're going to show how if you let theta equals pi and a equals the square root of 2, you can find the distribution of x plus y and x minus y. If you take those values of theta and a, then u turns out to be x minus y, v turns out to be x plus y. So that, in particular, that gives us that u is normal 0, 2 sigma squared and v is normal 0, 2 sigma squared, telling us that if you take the sum of two normal random variables, or the difference of two normal random variables for that matter, you get another normal random variable with the mean equal to the sum of the means of the individuals and the variance equal to the sum of the variances of the individual random variables, which you've probably seen before if you've taken statistics classes in the past, but that's one way that you can prove it. We'll show an easier way here in a minute. Oh, next example, say that we want to find the ratio of two independent normals. As you'll recall, I mentioned a few weeks back that if x and y are normal 0, 1, then the ratio of x over y, it has a Cauchy distribution. So how can we prove that? Well, let's define u to be x divided by y and v to be y. So easy enough to find the inverse of mapping of that. It's x is equal to u times v, and y is equal to v. So to find the Jacobian, take the partials of the expressions for x and y with respect to both u and v, then take the determinant of that, we end up with v. And the range of both x, y, and u, v is all of R2. So, the joint PDF of x and y, as we've seen various times earlier, is just 1 over 2 pi e to the minus x squared plus y squared over 2. And so to find the joint PDF of u and v, then we substitute uv for x and v for y, and then multiply by the Jacobian, the absolute value of the Jacobian, which is the absolute value of v in this case. We end up with absolute value of v over 2 pi times e to the minus u squared plus 1 times v squared over 2. So to get the marginal of u, we integrate that joint density with respect to v. That's of course equal to 2 times the integral from 0 to infinity. That's, I just used symmetry to the fact that it's a symmetric function or an even function, as we say, to change it from minus infinity to 2 times the integral from 0 to infinity. That gives us v over 2 pi times e to the minus u squared plus 1 times v squared divided by 2. Oh. And if you look at that for a second, you can see that the expression inside has a relatively simple antiderivative with respect to v, that if you just pull u squared plus 1 outside of the function, or minus 1 over u squared plus 1 as the case may be, then the antiderivative of the part inside the integral sign is just e to the minus u squared plus 1 v squared over 2. That's evaluated from 0 to infinity. Plug in infinity, get 0. Plug in 0, get 1. So we end up with the marginal of u being 1 over pi times u squared plus 1, which, as you'll recall, is the PDF of a Cauchy random variable, so we've proven that the ratio of two normals is Cauchy. Woohoo. Any questions about these bivariate transformations of random variables? How do you well, it depends on the situation. That for this example, we just chose v to be equal to y to make the math easy. That if what you're really interested in is the distribution of u, it doesn't really matter how you define v to be. In other cases, you'd want to define it such that both u and v are some specific thing, in which case then you define them to be whatever you need them to be. Honestly, in general, if you're trying to find the distribution of the sums of random variables or things like that, I don't like doing it this way just because having to deal with the Jacobians confuses me every time, and there's other ways to do this. As you'll see here in a second, if there's a simple moment generating function or characteristic function, that's often the easiest. That doesn't work for every set of random variables though, but usually I would say 90 to 95% of the time when you're trying to find a distribution of some function of random variables, you're trying to find the distribution of the sum, and there's other ways to do that. Well, if you'll recall the last problem on the midterm, I mean, that was a sum of random variables, and that trick that I put in the solution to that problem works in general, that you can just say that for a discrete random variable, if you want to find the probability, if you say u equals x plus y, you can say the, like, probability x equals 0 times probability y equals u plus probability x equals 1 times probability y equals u minus 1, then just sum over those. And for continuous random variables, you can do an integration analog of that. And that's usually easier than messing with the Jacobians. But now we're going to discuss this general problem of, as I was just saying, that you have x and y that are independent. You want to find the distribution of x plus y. And this is something that you do end up using a fair amount of the time. And plus, I mean, well, pretty much everyone in this class, those who are planning to take the master's qualifying exam, or those who plan to take 760, which I think is probably everyone in the class falls into one of those two groups. This is something that they harp on a lot, so make sure you understand this, that I remember when I was preparing this class that several times, several people on the curriculum committee were like, yeah, they came through that class, they didn't even know how to take sums of random variables, we're completely failing. So make sure you know this so it looks like I taught you something this semester. So anyway, say x and y are independent, we want to know the distribution of x plus y. So as I said, that in general the CDF of this z would be the set of x and y such that x plus y less than or equal to z. I guess that's kind of duh, but so there's a couple different ways that you can do this. That you can do the bivariate transformation method, the method that I just outlined in the first section. As I said, I don't like that because then I have to remember this Jacobian stuff, which I try my hardest to forget. The other approach is this convolution idea. That was essentially the last problem of the midterm, essentially what I was just saying there, that if you want to find the PMF of a discrete random variable z, then you just sum over all possible values of x and y such that x plus y equals z. So for a fixed z, then you could take x equals 0, y equals z, x equals 1, y equals z minus 1, or in general, x equals x, y equals z minus x, sum over all those possible values. And there's an analog for continuous random variables that involves integration, and honestly, I'm not sure if I put any examples in any of my slides, which was probably an oversight on my part. I may try to add some for Thursday, just because it's a useful technique to know, plus it's something that they love to put on qualifying exams and stuff. So I should probably give you some examples of how to do this. But there's a section on it on Cassell and Berger in any event. And there's also this method based on moment-generating functions, which, if you can remember the moment-generating functions and the distribution has the nice form, is almost always the easiest way to do this type of proof. It's just that it only works in some cases. That, well, for example, say we want to find the sum of two independent Poissons random variables. That this is essentially the same example on the midterm, but I'll go through it again anyway. That, say we want to find the joint density of x. Well, we want to find the sum of xy, but first of all, we'll calculate the joint density, which of course is just the product of the marginals, or joint PMF, we should say in this case. So to find the distribution of x plus y, as you'll recall, we just do the same sort of trick, that for a given value of s, x plus y will sum to s if given some sort of x, that y is equal to s minus x. So the density for a given s, you simply take the sum of x equals 0 to s of the PDF for x evaluated at x and the PMF for y evaluated at s minus x. And if you pull the constant parts out of the summation sign here, then you end up with something that looks like sum from x to 0 to s of s choose x times lambda 1 to the x, lambda 2 to the s minus x, which, of course, by the binomial theorem, is just equal to e to the minus lambda 1 plus lambda 2 over s factorial times lambda 1 plus lambda 2 to the power s, which is, of course, just the density function, or the PMF for a Poisson random variable with parameter lambda 1 plus lambda 2. Saw this already on the midterm, but in general, that's another way that you can find the distribution of the sum of two random variables, just doing this convolution type thing. And as I said, I like that better than the bivariate transformation approach, just because you avoid having to remember the Jacobian business. It turns out, if you work out the Jacobian business in the general case, you end up with precisely this, but this to me is a little easier to remember, just because the idea of taking probability x equals 0 times the probability y equals s and summing up over that is just easier for me to wrap my brain around. And the other way you can find the distribution of sums of random variables, like I say, this is almost always the shortest and easiest way to do it when it's possible, is that if x and y are independent random variables with characteristic functions, then to find the characteristic function of x plus y, you just multiply the characteristic function of x and the characteristic function of y. And then if there's a simple way to go from the characteristic function of the some random variable to calculate the distribution of the z, then you're done and you don't have to go through any of these sums or integrals or any of that messy junk. And quick proof of this, the characteristic function of z is, of course, the expected value of e to the iz theta. Well, z by definition is x plus y, so that's the expected value of e to the I times x plus y times theta, which of course is just the expected value of e to the I x theta times e to the I y theta, and then by independence we can write that is e to the expected value of I x theta times e to the expected value of I y theta, which of course is just the product of the characteristic function of x and the characteristic function of y. And similarly, if x and y are independent and you want to find the distribution of x minus y, then you can just take the characteristic function of x evaluated at theta times the characteristic function of y evaluated at minus theta. So let's do the Poisson example again, but this time using characteristic functions, so we don't have to try to do that sum and try to remember the binomial theorem and all that stuff. Oh, the characteristic function, as you'll recall, the characteristic function of a Poisson random variable with rate parameter lambda x is just e to the lambda x times e to the theta minus 1. So the characteristic function of z will just be the characteristic function of x times the characteristic function of y. And that, of course, is just equal to e to the lambda x plus lambda y parentheses times e to the theta minus 1. And didn't write the punchline here, that of course is just the characteristic function of a Poisson random variable with rate parameter lambda x plus lambda y. Woohoo, we're done. You're right. That I think this is actually moment generating functions that I should have either written moment generating functions or included the i's. I'll try to remember to fix that and upload updated slides. Good catch. So now let's do the same thing for normals. We have x is normal with mean mu x sigma x squared, y is normal with mean mu y sigma y squared. If you've taken statistics before, you may have learned that their sum is just normal with mean mu x plus mu y and variance sigma x squared plus sigma y squared. Well, how can we prove that? Well, I mean, you can do the integral where the type of convolution double integral analog of the summation we did earlier, but personally I like to avoid integration whenever I can, particularly if I'm doing an exam and time is of essence, so can we do this faster? Well, recall the characteristic function of x and the characteristic function of y is just e to the I times mu x times theta minus sigma x squared times theta squared over 2. Likewise for y, so we combine those two terms together, we end up with e to the I times mu x plus mu y theta minus 1/2 sigma x plus sigma y squared times theta squared, which, once again, that's precisely the characteristic function of a normal distribution with mean mu x plus mu y and variance sigma x squared plus sigma y squared. So once again, now we're done. Don't have to do any more convolutions or anything to come up with the distribution of x plus y. And say that we want to find the distribution of two independent gamma distributions where there, come to think of it, there's another typo. The x should be gamma alpha sub x. They shouldn't both be alpha sub y. I'll try to remember to fix that one as well. But, and say we want to take the sum of x and y. Here, note that the rate parameters are different, but the shape parameters are the same. The shape parameters are different in general. This doesn't work, but that here and once again, we're missing i's. I think I wrote moment generating functions. I apologize for not proofreading these slides more carefully. Like I said, it's actually kind of funny, the history of these slides. I got these from Mike Wu, but he actually got them from one of my friends from grad school who is now at NC State, who I ate dinner with last week. It was kind of funny. We're using practically the same slides for our Casella and Burger class, but so that's my lame way of saying that it isn't my fault there's so many typos. But anyway, so in this case, the moment generating functions look like that. The characteristic functions would be essentially the same thing, only you insert some i's in there. Oh, obviously, you multiply that together, it's just 1 over 1 minus beta times theta, the power alpha x plus alpha y, which is, of course, gamma distribution with parameters alpha x plus alpha y. So, in particular, as you'll recall, if alpha equals 1, then you have an exponential with parameter beta. And if alpha equals n over 2 and beta equals 2, that's a chi-square distribution with n degrees of freedom. So, what we just showed is one way to show the sum of chi-squareds of a chi-squared with n1 degrees of freedom and n2 degrees of freedom is a chi-squared with n1 plus n2 degrees of freedom, which should agree with our intuition given the definition of chi-squared, but that's one way that you can prove it. Any questions about any of this before I go on to conditional expectation? Okay, I'll try.
Sorry. So in this case, if it's not already in like a form that we know, there's no way to go from like the characteristic to a distribution. Is that right?
What do you mean, a form that we know?
Well, like in this case, like you can tell that that's already like the gamma characteristic.
Yeah, that to do this, number one, you need to know the characteristic function of the distribution that you're looking at, and that hopefully it has a nice closed form. If you don't have the characteristic function, calculating the characteristic function may be more trouble than simply doing the convolution to calculate the distribution of the sum directly. And even if you know the characteristic function, you need to have the product of the characteristic function have a nice form to be able to go backwards once you have the characteristic function of x plus y. That, for example, if the betas are different here, then you end up with a product that there's no good way to simplify, so it doesn't really help you find the original distribution. So this entire technique of using characteristic functions or moment-generating functions, it's really slick and will save you a ton of work when it works, but quite frequently it won't, in which case you have no alternative to doing ugly integrals. And like I said, I'll try to remember to include some examples of the convolution argument for continuous random variables on Thursday or something like that. That really should be in the slides because it's a technique that's useful a fair amount, and it's something that the powers that be in this department really want you to know for whatever reason. Okay, on to conditional expectation. This is another thing that I've always just kind of struggled with just because I find it not very intuitive, and I think where you use this the most is for like Bayesian type modeling, which I don't do a ton of, so that may be another reason I always have a hard time wrapping my brain around it. The slides actually did a pretty good job here of giving examples showing why this would work and why you want to use it, so hopefully it makes sense. But to define conditional expectation, it's basically, recall the conditional distribution of y given x. It's that assuming we know that x is equal to something, we want to find the distribution of y for that specific value of x. And we talked about how you can calculate the conditional distribution of y given x. Well, we could then define the conditional expectation of this conditional distribution, that for some given y, the conditional expectation is just sum of y times the value of the PMF for the PMF of y given x summed over all possible values of y, or if y is continuous, then we would do the analogous definition in terms of integration. Note that this is a function that depends on x, so you can define a random variable x to be the conditional expectation of y given x. And in particular, that if you just let x equal to some fixed constant that we call little x, then the expected value of g of y given random variable x is just this conditional expectation evaluated at whatever value of x. Probably obvious, but anyway. And said for continuous random variables, it's just the obvious analog to discrete, that rather than summing over all possible values of y, you just integrate over all possible values of y. So anyway, an example of this, say that you're doing like a biology example, you have a cell, it takes a certain amount of time to undergo mitosis, basically means that it splits in half, and creates two daughter cells, so you wait a little longer and then one of the daughter cells divides. And so obviously the total amount of time for both the first cell and its daughter cell to divide will just be x plus z, and we'll just assume that x and z both have an exponential distribution. So given the value of x greater than 0, the distribution of y, the sum of the two, is just a shifted exponential random variable with PDF lambda times e to the minus lambda y minus x, where y is obviously greater than x. And the conditional expectation of y, given that x equals x, you just integrate this condition, you just integrate this conditional PDF from x to infinity. Integral's relatively straightforward to compute. You end up with x plus 1 over lambda, which should make intuitive sense. As you'll recall, the expected value of exponential random variable in general is 1 over lambda. So this is saying the expected value of this random variable y, that's x plus z, given x. We know what x is, and then we add z, which is a random variable with expected value 1 over lambda. So the expected value of their sum is just the value of x that we've already observed, plus the expected value of z. And so if we want to define this in terms of x, then the conditional expectation of y given x is going to be x plus 1 over lambda. And you could also compute this, as I said, directly by just taking the definition of y. The expected value of y given x is just the expected value of x plus z given x, which we split up into two pieces. The expected value of x given x, well, given x, x is just a constant, so that's equal to x, and then the expected value of z given x, which, as I said, z and x are defined to be independent, so the expected value of z given x is just the expected value of z, which is 1 over lambda. And you can show in general that if x and y are any two random variables, then the expected value of x is always equal to the expected value of the conditional expectation of x given y. And I always have trouble wrapping my brain around this formula, even though it's relatively simple to write down, but I'll go through the proof and hopefully that will make it a little bit easier to see. The expected value of x given y is, of course, equal to expected value of x given y. As I said before, that's a random variable in terms of x. So now we take the value of that random variable times the distribution function of y, integrate with respect to y. Well, how is that conditional expectation defined? Well, the definition of that conditional expectation is that it's the integral of x times the conditional density of x given y, e evaluated at x. So then we combine those two integrals. We get x times the conditional density of x evaluated at y times the marginal density of y. And as you'll recall, the definition of the conditional density is that it's just the joint density divided by the marginal. So it's the same sort of thing. The probability of A and B equals the probability of A given B times the probability of B. That's the same thing here. We basically have the probability of X given Y times the probability of Y, which is just the probability of X and Y. Well, that's the double integral of f of x and y times x, which of course is just the definition of the expected value of x. So, yeah, as noted here, the expectations are with respect to different variables and different densities. It's a little confusing, but that's the way you do the proof. So, back to the cells example, we showed earlier the expected value of y given x is x plus 1 over lambda. So if we find the expected value of this expected value, we end up with the expected value of x plus 1 over lambda, which is of course the expected value of x plus 1 over lambda plus 1 over lambda, which is 2 over lambda, and based on the results of the previous slide, that should be equal to the expected value of y, which it is. Y is just defined to be x plus z, so that's the expected value of x plus the expected value of z. 1 over lambda plus 1 over lambda is 2 over lambda. Oh, here's an example of a hierarchical model where where this sort of thing comes in handy. My understanding is the more complicated versions of this approach are often used for Bayesian modeling and things like that. That say that you have an insect and the number of eggs that the insect lays has a Poisson distribution, and the probability that a given egg survives has probability p. We'll also assume the survival of eggs is independent of one another. So what's the average number of eggs that survive? So then we know that the distribution of y, which is the number of eggs that the insect lays, is Poisson, and x is the total number of eggs surviving. The distribution of x by itself is kind of difficult to calculate, but we know that the distribution of x given the number of eggs, or given y in that case, we know it's binomial with number of trials y and probability of success, which in this case is the probability of survival p. So to find the marginal distribution of x, then we can take the joint density of x and y and sum over all possible values of y. And that joint density can be written in terms of the marginal density for y and the conditional density of x given y, both of which we know how to calculate. So the conditional distribution of x given y is binomial. That has the PMF that we write below here inside the square brackets. The marginal distribution of y is of course just the marginal PMF of the Poisson in the second set of brackets. So if we can try to simplify that expression by first of all taking the terms that don't depend on y outside the summation sign, inside the summation sign, we end up with the sum from y equals x to infinity of 1 minus p times lambda to the y minus x divided by y minus x factorial, which you may recognize that infinite sum is just the Taylor series for e to the 1 minus p times lambda. That, if you don't follow that, it might help to rewrite it from y equals 0 to infinity by subtracting x from everything, or you can just take my word for it, that's just a Taylor series there. So you end up with a marginal PDF of x looking like that. And that, of course, can be written as lambda p to the x times e to the minus lambda p all over x factorial, which of course is just a Poisson random variable with rate parameter lambda times p. So the expected number of eggs that survive is just lambda times p. So even though, well, that shows how we can find the marginal distribution of x and hence the expected value of x given the marginal PDF of y and the conditional PDF of x given y. It turns out to still be Poissons. I mean, it's kind of cool, but anyway. Another way that you can do this is to use the iterative expectation formula. If all you care about is the expected value of x and you don't care about the distribution of x, then you don't have to go through all that summation and hope that you remember how to see the Taylor series and so forth. If all you care about is the expected value of x, well, then you can just take the expected value of the expected value of x given y. Well, we know the expected value of x given y is y times p. Oh, take the expected value of that with respect to y, we end up with just lambda times p. That's much easier than dealing with all this summation business. So now, let's say that there's several different insect mothers, each with different average number of eggs. So we'll assume that we choose some mother at random, and this particular mother's Poisson rate parameter is going to be exponential. We call, I don't even know what that Greek symbol is. Is that a lambda?
That's capital lambda.
Is that a capital lambda? Okay, well, glad my students are smarter than I am. It's a Poisson with exponential random variable lambda that has mean parameter beta. So what's the expected number of eggs surviving now? Well, we can use the iterative expectation formula again. The expected value of x is the expected value of the expected value of x given y, which is the expected value of p times y, which to find the expected value of y, that's the expected value of p times y given lambda, which is then the expected value of p times lambda, and the expected value of lambda is, in this case, has mean parameter beta, so we end up with the expected value being p times beta. Oh, again, in this case, I would not even want to attempt to calculate the marginal PDF of x here. That maybe it's not as messy as it would appear, but I wouldn't want to work through all the algebra anyway. But using this iterative expectation formula, we can calculate the conditional distribution of x without ever bothering to figure out the density of x, just using the fact that it's relatively easy to compute these various conditional densities. Oh, p is given that that's the probability of that an egg survives. So given the number of eggs y, then x is binomial with distribution with y trials and probability p of success. So yeah. Now we'll talk about conditional variance briefly. But say we have random variables x and y. If you recall, the definition of the marginal variance y, or in general the marginal variance g of y, is just the expected value of g of y minus the expected value of g of y squared. And so we can define conditional variance similar to the way that we define conditional expectation, that if you want to find the conditional variance of y given x, that's the expected value of y minus expected value of y given x squared. All of that's given x. And both of these expectations are taken with respect to the conditional PMF or the conditional PDF. And just like conditional expectation, the conditional variance of y given x is a random variable whose value depends on x. And there's this formula for conditional variance that I can never remember precisely. It's the sort of thing you may want to put on a formula sheet for a qualifying exam, because it's one of these things that sometimes there's like some convoluted thing that's impossible to take the variance of unless you use this, but it's not the sort of thing that one can easily remember. And I'll show here in a second that for any random variables x and y, you can always write the variance of x as the expected value of the variance of x given y plus the variance of the expected value of x given y. Oh, how do you prove this? Well, the variance of x is by definition just x minus e of x squared. And now we'll just add and subtract the expected value of x given y in the middle of that expression. This is just one of those non-intuitive steps that you do because once you do it, then all the math works out. And so then you square that and simplify the algebra, and you end up with three different pieces. That first piece is x minus e of x given y squared plus the expected value of e of x given y minus e of x squared plus this last piece down at the bottom 2 times x minus e of x given y times e of x given y minus e of x, blah. Well, let's just look at these pieces one at a time. We'll show that the first two pieces sum up to the two pieces in the conditional variance formula, and the last piece goes to 0. So, first piece, the expected value of x minus e of x given y squared. Well, using the iterative expectations formula, we can write that is e of the whole thing given y, which is just the very definition of the expected value of the variance of x given y. So we've now proved the first piece of this expression. So now the second piece. That expectation, once again, rewrite the expected value of x is the expected value of x given y using the conditional expectation formula once again. And that is just again, is the definition of the variance of the expected value of x given y, because we have the expected value of x given y, which you'll recall is a random variable depending on x, minus expected value squared, then taking the expected value of all that. That's just the definition of the variance. So now the final piece. Expected value of x minus e of x given y times expected value of x given y minus e of x. Well, once again, using the iterative expectations formula, that's the expected value of everything inside given y, and rearrange the terms then that gives the expected value of x given y minus expected value of x times the expected value of x minus e of x given y. So then the second piece can be rewritten as the expected value of x given y minus expected value of x given y. Well, expected value of x given y minus expected value of x given y is, of course, equal to 0. So when you multiply the whole thing together, it goes to 0. So, yeah, that's kind of an annoying proof because you have to take a number of steps. But it's just like, how did you think to do that? And hopefully they would never be evil enough to put that on a qualifying exam or something, because it's just a proof that you're not going to be able to do if you don't have it memorized. Oh, anyway. Recall our Poisson binomial hierarchical model, our insect example, that y is Poisson with rate parameter lambda, and the conditional distribution of x given y is binomial with y trials and probability p of success. We showed the expected value of x is lambda times p. Say we wanted to find the variance in the number of insects that survive to adulthood. So that would give us, we can use the conditional variance formula. That's the expected value of the variance of x given y plus the variance of the expected value of x given y. Well, the variance of x given y, we know that x given y is a binomial random variable. So the variance of x given y is just y times p times 1 minus p, and the expected value of x given y is just y times p, using the formulas for the variance and expected value of a binomial distribution. And now we know, and now y is just a Poisson, and we know that both its expected value and its variance are both equal to lambda. P is constant, so we can pull all that outside the expectation sign. We end up with p times 1 minus p times expected value of y, which is lambda. So in other words, lambda times p times 1 minus p plus the variance of y. Variance of y is lambda. If you pull the p outside the variance sign, you have to square it, because in general the variance of c times x is equal to c squared times the variance of x, so we end up with lambda times p squared. Simplify that term, we end up that the variance of x is equal to lambda times p. So, and that's consistent with what we got earlier, where we showed that x has a Poisson distribution with rate parameter lambda times p. But if we didn't want to go through all those calculations to calculate the conditional distribution of x, then we could have just, if we didn't want to go through all that to find the conditional distribution of x, we could just use this conditional variance formula to compute the variance of x that way. So, any questions about anything else today?
You're going to have your regular on
Yes. And as usual on Wednesday, I have a conference call at 5, but I mean, in principle, if anybody wanted to meet me after that conference call was over, that's fine as well, or before my office hours, whatever.